Okay, so good morning. So we continue this topic of oscillations of non-conservative systems. So the topic is about solving the system which is governed by these equations of motion, Euler-Lagrange equations on the left-hand side, and then there are some extra forces which we call external on the right-hand side. We assume that the forces depend on positions and velocities. And just recalling that Lagrangian is the sum over all. So here is I, right? So there are n equations. So where n is number of degrees of freedom, so n degrees of freedom, then the Lagrangian function is sum over 1/2 mass factors by velocities minus potential energy. So this is standard. And then what we saw is that we can write an equilibrium condition for the equilibrium. So equilibrium solution is a solution which is a constant in time, and we saw that condition for the equilibrium is that the forces, internal forces, they equilibrated by external forces. So better writing with arguments. So the internal forces plus external forces at the equilibrium. So the position and zero velocity balance each other. Right? So just remember what is internal. So internal force component I is just minus u, derivative of u with respect to component q. So that's by definition. So this is equilibrium condition. And then we found the linearized system. System near the equilibrium. So we consider all the deviation from the equilibrium, that q minus q0, its derivative, second derivative, etc., are small. So we assume that they are small, and we keep only linear terms in equations of motion. So we take this equation of motion. We know that it's satisfied at the equilibrium. So the zero order terms cancel each other. So then next order terms are linear terms. So we keep these linear terms, and the quadratic, cubic, and higher order terms we all neglect. So when we do this, we get the system which is the linearized system, and it has a form m delta q double dot plus l double q plus q double q equals 0. So this is a linearized system. And I just recall you what are the matrices. So matrix M is just the matrix, mass matrix at the equilibrium. Then L is the minus Jacobian matrix of the external force with respect to velocities, so this should be computed at the equilibrium, right? And then this K matrix is C minus Jacobian with respect to coordinates, and C is a Cij, is a matrix where components are second derivatives of the potential. Also at the equilibrium, right? So important is that we have linear equation with three matrices, M, L, K, and these three matrices are defined by the original system. So these are just linear terms. So okay, so that's what we have, and the idea is that we cannot solve the original system, and we even still don't understand all the properties of these general nonlinear systems. But we can complete. But if we assume that we are near the equilibrium, so all the deviations are small, so it's just small oscillations near the equilibrium, then we approximate this system by the linearized system, and this system we can solve. So today will be a rather complicated lecture, which is we will just focus how to solve this equation, nothing else. So properties of these solutions we will see later, but today we will see how to solve equations of this type in general. So we find a general solution, and that's not so simple because it's based on the central result of the linear algebra, which is Jordan theorem. So essentially, we will repeat all this. We will try to understand all these properties. In linear algebra, this is difficult topic, but we will not have. We will make derivations, but we will not prove the central theorems. So let's make it possible. So the question is how to solve. And the key point is that we can solve. So unlike the original system, this we can solve. So what we do? So the first way is just let's start in the same way as we did with conservative system. Remember, with conservative system we didn't have this term, and this was C symmetric matrix. So we consider particular solution. Let's consider particular solution. So it will be in the form exponent lambda t by, I will use capital U here, by capital U. So the vector and exponent. And remember, just the same way. So this system is linear with real coefficients. So we can solve it both in real variables and in complex variables. Doesn't matter. So complex variables also work. And whenever we compute complex solution of in complex variables, it's a real part and imaginary part. They give two different solutions. So kind of solving it in complex variables, we get two solutions. So if we want to find particular solution in complex variables, we may have two solutions if it's complex. So what we assume is that lambda is a complex number and u is a complex vector. Okay, so that's called eigenvalue. This will be called eigenvector. So the first step we'll do is we substitute this expression into the equations. And now everything is so this is delta. So now everything is becoming simpler because differentiation with respect to time just give lambda. The time derivatives gives lambda squared. So what you get, m. So second derivative will give you lambda squared. First derivative just gives lambda. Oops. First derivative just gives lambda. Okay, so first exponent is just a number, real number, which is not zero, complex number, which is not zero. So we can cancel. And then we put u outside because every matrix is multiplied by the same vector u. So what you can get, you get lambda squared m. From here you get lambda L. And k from the last vector, u equals 0. So this is what's called eigenvalue problem. Eigenvalue problem. So that's an equation. So if you get any pair of lambda and u which satisfies this equation, you get a solution. And that's an idea. Okay, now the next step is that we can split the problem of finding, split the problem of finding eigenvalue from the problem of eigenvector. So what you can see that if the vector is non-zero, it multiplies the square matrix. So if the vector is not zero, we know from linear algebra that the matrix must be singular. Okay, singular means the determinant is non-zero. That is, and now we get just equation for eigenvalues. So this is called characteristic equation. Characteristic equation. And what it is, remember that so determinant is a product of n components, different n components, sum of different products of n components of the matrix. Each component is square in lambda. So this is a polynomial of degree 2n. It's called characteristic polynomial, so polynomial of degree 2n. And polynomial of degree 2n has 2n roots. So we have from it, so it means that we have 2n complex roots. Counting multiplicity. Good. And to each of them we can give eigenvector. So with the eigenvectors. So if lambda is 0, automatically we have a non-zero solution. Okay, so so this means that we can take that it means that we have 2n particular solutions. And these are complex solutions in general. And since the problem is since the problem is linear, so the equation is linear, we can take linear combinations. So we can find a solution in the form of linear combination of these solutions. So we can multiply each solution by a complex number. And this will be a family of solutions. But family solutions. Okay, in general, complex. And if you want to have a real solutions, so the real part of this sum or imaginary part of this sum are real solutions. So now there is a question. So did we solve the problem? So is it a general solution? So unfortunately, the answer is generally not. So in fact, this way we can. It's not always the case that in this way we can find a general solution. Actually, there are two situations. So that if all eigenvalues are distinct, so if all of them are different, then yes. And if some eigenvalues are multiple, so if there are some equal numbers, equal roots in this sequence, then sometimes yes, sometimes not. So I'm not going to prove these two things because it will follow from what we do just next. But the idea is that you can follow the same idea the same way as we did in conservative system and form the equation as a sum of these particular products of exponent by a vector. So eigenvalue or by time, exponent of the eigenvalue by time by eigenvectors, taking the sum. So it turns out that in principle, this is a good way, because if you are lucky that all eigenvalues are different, this is a general solution. We will see why. But if some eigenvalues are not equal, and this is a situation in many, this is a situation that you encounter in many important cases, then this is not a general solution. Something is missing. Sometimes missing, sometimes not. So today we want to understand how, in principle, you guarantee that the solution is general, how you find it, and why sometimes it is a solution, why sometimes it's not. Okay, so what you do? So we proceed in a different way. So we proceed in a different way. So we essentially look for this solution, but not this form of the solution, but not for this problem. We will transform it. And we will transform it in some objects that we used to in a series of differential equations. So what we do, we define the new variable as a velocity. So we say velocity will be our new variable. So then what you have? Then instead of second derivative of delta Q, you can write first derivative of capital Q and just capital Q here. So now you can put everything to the other side. Let's start from the last. And then mass matrix is always, remember, it's positive definite, so it's invertible. So we can just put mass matrix on the other side with an inverse m minus 1. Good. So now we have two equations. So we have this and that, and we can write them together. So let's write it, flip the first, and keep the second. So we have a system. So the next step is we say that vector x will be vector which is constructed by two vectors that you put on top of each other. So now it's in dimension, we call it capital N, so capital N is twice small n. Right? So we take vector of coordinates, vector of velocities, and put them together and form a single vector. And then we can write this system as x dot equal ax, where A is a matrix. So you see what is a matrix. A. So on the first line you have to you should have Q. So if you to have Q here, you put. So this is matrix which is n by n. So which means 2n small n by 2 small n. Right? So we can divide this matrix onto 4 blocks, n by n. So in order to get Q capital here, you have to put 0 matrix here and identity matrix there. Right? So identity is matrix which has ones on the diagonal. So then you multiply x by this matrix, delta Q cancels, and this capital Q stays, and then you get this. So on this, here you should put this matrix, minus m minus 1k, and here you should put minus m minus 1l. Okay. Good. So I just wrote the original system which we had in the form of the second order, in the system which is first order, and this is an object that it's classical object that's studied in differential equations. So this is a system of linear differential equations with constant coefficients. So we will solve this equation. And solving this equation with this matrix is just the same as solving the original equation because they're equivalent. So if you have solution x, then solution of the previous one is the first n component. And the vice versa, if you have solution of the first one, then you can take coordinates and velocities and give the solution to that. So there is one-to-one correspondence of the solutions. So instead of solving this, we can solve this, and this is just the same thing. Okay, so the first. We will go the same way. We will look for particular solutions, and just in the same form. So particular solution. We take the solution as exponent lambda t, and then here we use small u. So lambda is complex, and u is complex vector in dimension capital N. So just the same story, because that's a linear equation with real coefficients, because A is a matrix of real numbers, and we can solve it with complex x. It doesn't matter if x is real or complex. And whenever you have a complex solution, the real part is the solution, the imaginary part is the solution. So again, this is called eigenvalue. Just for you to remember, this is eigenvector. So now when you substitute it to the equation, x dot is lambda e lambda t u, and it should be equal to a x, which is a e lambda t u. So exponent again can be cancelled, and then we'll take these two, just flip. And this is a classical form of the eigenvalue problem for the matrix. Whenever you have matrix, so this is what's called eigenvalue of the matrix, and u is what's called eigenvector of the matrix. Okay, another form you can write, you can put everything to the left and write it as a minus lambda identity u. Right, so identity by u is u, a u minus lambda u equals 0. Just the same form. But now this is square matrix by a vector. And in the same way, so if u is non-zero, because zero vector is not our interest, then the matrix should be singular. So again, we get characteristic equation. With the left-hand side is characteristic polynomial of degree the same as the size of the matrix, so n. Which gives you two n roots, or capital N roots, counting multiplicities. So just the same as we had before, exactly the same roots as this. Problems should be equivalent. So we had two n roots, two small n roots, and we get two small roots, but just in a different way. And we can also have, and we can, to each of them, you can compute eigenvector. Just by solving this equation, because whenever matrix is singular, you can find eigenvector. So the problem is that these vectors may be not linearly independent. So not a basis. So the problem is that in general, for arbitrary matrix A, you do not guarantee that you can form a linearly independent set of vectors. We will see example. And if you don't have linearly independent set of vectors, so surely by these solutions you cannot form general solution. Because you cannot satisfy arbitrary initial condition. So what then you do? So the first is useful observation that if all eigenvalues are distinct, so all of them are different, then eigenvalues are linearly independent. So everything is all right. Then taking the sum of them is a general solution. Because you can satisfy, so if you compute it at 0 time, this will be just sum Ci ui. So this is a basis expansion. Right? So if eigenvalues are different, that we know that eigenvectors are linearly independent. This follows from linear algebra. I'm not proving this. So the good case is when eigenvalues are different, then you take just all the eigenvectors, and you form linear combination, and you find a general solution. Okay, so this is fine. So the problem is when eigenvalues are multiple. So the problem is when eigenvalues are multiple, which means that when there are some of them are equal in this sense. So remember that you obtain eigenvalues as the roots of the polynomial. Yes, there are n of them, but some of them can be equal. So what to do in this situation? So let's first give some definition and see some examples. Example of what may happen. And before doing this, let's put another observation. So let's consider this situation. So first, let's finish with this first part. So the first part is that you can find a general solution which is complex. So everything is complex. So how you find the real solution? So how to find a general real solution if all of them are distinct. So we just show that whenever all lambdas are different, this gives you general complex solution. It satisfies general complex initial condition. So now, how in general we don't want any complexity in the final result, right? Because our system is real, initial conditions are real. So what we do? So there are two cases. So if lambda is real, then also the eigenvector is real, right? Because whenever eigenvalue is real, you can solve this problem with a real eigenvector. Now, if lambda is complex, so sigma plus I omega is complex, then eigenvector also must be complex. So this is I. No? And what we do, we write the complex eigenvector as V plus I double. So the sum of where now V and W are real vectors. Just separate real and imaginary part. So okay, so in this case is a real solution. So we don't. So in case of the real eigenvalue, real root, we don't have to do anything. But what we have to do if the root is complex. Okay. So what you do? What you do is just write solution. Is exponent lambda t u. So now we can write it as exponent of this complex number. So it will be sigma time by cosine omega t plus I sine omega t, right? By u that we write as v plus I omega or iw. Then you open this product. So you have exponent lambda or sigma t by cosine omega t v minus sine omega t w. So that's the real part, and then plus I took a product, open the product. And then we have two solutions. So this is real solution 1. And this is real solution 2. Whenever you have complex eigenvalue with complex eigenvector, you get two solutions. Which is in principle good because you have more solutions, but at the same time it's a bit worrying because we have for each complex eigenvalue we get twice more solutions. So we have actually too many solutions. But it turns out that it's not too many because if lambda and u of this form are eigenvalue and eigenvector, then what you can do? Then remember what means eigenvalue, eigenvector. They satisfy this equation. But what you can do, you can make complex conjugate of both sides. If you make complex conjugate of both sides, then you find that A complex conjugated is A, because A is real. Then you have complex conjugated U equal complex conjugated lambda conjugated U. So what you find that then in that case, so the lambda conjugated, which is sigma minus I omega, and U which conjugated, which is V minus W IW, are also eigenvalue and eigenvector. Right? So whenever you have eigenvalue, eigenvector, which are complex conjugated eigenvalue, eigenvector, they also conjugated. They also eigenvalue, eigenvector. So actually, what you can also see that the same solutions, solution 1, solution 2, follow considering this couple. So if you now start with lambda conjugated, U conjugated, all you change is minus here, so you essentially get the same two solutions. So it means that pair lambda U and lambda complex conjugated U conjugated, two solutions gives two real solutions. So two complex solutions which correspond to pair gives two real solutions which correspond to the same pair. So essentially this is just different way how to write a particular solution. So a pair of complex conjugated solutions, or in the complex form, they can also be associated to the two real solutions. So a general solution is so let's call it case A, case B. Is a linear combination of solutions U for real eigenvalue, eigenvector, and solution 1, 2 for complex eigenvalue, eigenvector. So whenever you have a real eigenvalue, you take just solution as it is. And whenever you have complex eigenvalue, you have these two pieces, and taking linear combination with arbitrary coefficient gives you a general solution. So we will not verify. So in the same way, so you see we verified that this is a general solution because we know it's a solution and we know it can satisfy arbitrary initial condition complex. So in principle, it automatically follows from the previous condition almost automatically, but you can verify it directly. So that if you take these sums with this and that, you can satisfy arbitrary initial condition. Okay. So that's it. Make a break. So essentially, before making a break, just to say that we see that whenever eigenvalues are all different, there are no problems. So we can solve it just in the same way as we did before with the conservative system. It's slightly, there is slight difference if you want to write solution in a complex or real form. But in principle, you find eigenvalues, we find eigenvectors, take a sum, and you get different solution. So the only problem which we can encounter is when the eigenvalues are multiple. And this is rare, because usually if you take any matrix, it's usually has different eigenvalues. But this is important because it corresponds to many important situations in various fields, because eigenvalues they appear not only in oscillations but in many other fields of mathematics, physics, and chemistry, whatever. And okay, so we want to solve this problem completely. So not only in the case when eigenvalue is different, but now what happens if they are multiple? And this will let's try to do it after the break. Okay, so break. Okay, so we try to understand now multiple eigenvalues. So that's a complicated issue. So we will I will actually try in 1 hour to give a overview of probably the hardest part of this linear algebra course that you usually have, but without proof. So just the main idea, which I think is enough for understanding what happens, but it's not that simple. So first of all, what is it? So we have a eigenvalue problem, and associated to this eigenvalue problem, we have the characteristic equation, which defines eigenvalue. So this is just polynomial of degree n. So what means eigenvalue is multiple? It means that when you factorize this polynomial, it appears as a root several times. And this number of how many times it appears as a root, it gives you multiplicity. So that's usually called Ka. So we will call it Ka. So it's algebraic multiplicity. Algebraic because we obtain it from algebraic formulation from the polynomial. So S a root, so S a root of characteristic equation, characteristic polynomial. So we have characteristic polynomial. If it's, for example, second order, then it's lambda minus 2 squared. Then 2 is eigenvalue which appears twice. So it will be algebraic multiplicity will be 2. So we will have example right now. But then there is another way, which is eigenvalue problem in the vectorial form. And this eigenvalue problem can give you another type of multiplicity, which is geometric. And this is a number, is a maximum number of linearly independent eigenvectors. So how many eigenvectors you can find for the same eigenvalue? Like 1, 2, 3, and 4, and so on. So how many linear eigenvectors, independent eigenvectors you can find for the same eigenvalue? So this gives you geometric multiplicity. Why geometric? Because essentially you see that all eigenvectors for the given eigenvalue, all eigenvectors form a linear space. So what Kg is a dimension of this space, in other words. But in a simpler words, it's just maximum number of linearly independent eigenvectors. So just the same thing. So let's consider 2 examples to see that this is not the same thing. Not always the same thing. So first example will be, just consider matrix 0, 0, 3, well, diagonal matrix with 3 on the diagonal. Okay. Characteristic equation. It means that we have to subtract lambda from a diagonal. So that's product of these 2 minus product of these 2. It's 3 minus lambda squared should be equal to 0. And you get that there are two eigenvalues. So the eigenvalues, two roots, which are both equal to 3. Right? So this means that we have a multiple eigenvalue with algebraic multiplicity 2. So the eigenvalue 3 has multiplicity, algebraic multiplicity 2 because there are two roots. Okay, the next is, but what is geometric? So geometric means that we have to solve this eigenvalue problem. Let's write it in this form. So the eigenvalue problem. So now it's not a determinant. So what stays here is this matrix with lambda equal 3. So put in lambda equal 3. This is just 0 matrix. And this means that we can find two linearly independent eigenvectors. 1, 0 and 0, 1. So geometric multiplicity is always 2. Is also 2. So we have the same algebraic and geometric multiplicity. Okay, this is first example. So the second example, take the same matrix, but let's put 2 here on the corner. So first is a characteristic equation. So we have to add 2 in the corner. So it's product of these terms by these terms, so there's nothing changed. So we have the same eigenvalue and the same multiplicity, algebraic multiplicity 2. But it's not so. But what happens with the eigenvectors? For eigenvectors, when we take lambda equal 3, so you see it will cancel diagonal, but will stay. But 2 will stay. So the matrix will be 0, 2, 0, 0. And for this problem, you can just find one eigenvector. It's 1, 0. So you see that geometric multiplicity here is 1. And it's not the same as algebraic. So what we will see in a theorem that I will formulate later, first of all, we will see that always geometric multiplicity is always big or equal than 1, because one eigenvector you can always find. But it's smaller or equal than algebraic multiplicity. So that's a non-trivial inequality. So you can never find more eigenvectors than the algebraic multiplicity. So there's a number of roots as a roots of polynomial. So the number of eigenvectors is at most as the number of roots, but can be smaller because here it's exactly smaller. So that's a general situation. And so when Kj and Ka are both 1, so when they both equal to 1, then we say that eigenvalue is simple. So there is nothing special about this eigenvalue. It's just 1 as a root, just one root and one eigenvector. So nothing more interesting happens. And when kj is equal to ka bigger than 1, we say that lambda is semi-simple. So semi-simple, why? It's because, okay, it appears several times as a root, but to each of the roots we can give eigenvector. So so what happens when kj is smaller than ka? And this is exactly the problematic case. This is a problematic case. So this is a problematic case because exactly in this is a case when we cannot form a general solution out of eigenvectors because there are not sufficiently many eigenvectors. We don't have a basis for eigenvectors in this situation because there are more roots than eigenvectors. So eigenvectors cannot be just, so in this case, eigenvectors do not form a basis because there is a deficiency in an eigenvector. So you have, like, for example, like in this case, we have two roots, but just one eigenvector. And you cannot, with one eigenvector, form general solution. So in this case, so what happened in this case? In this case, there is a extension of this idea of eigenvector to the concept of generalized eigenvector. Or the Jordan chain. So there is a generalized concept of what is an eigenvector, and how we do it. So instead of our eigenvalue problem, which was written as AU equal lambda U, we consider a chain of equations. So first equation will be just the same for the vector U1. So this is eigenvalue problem. So this is original eigenvalue problem. But then we make the next one, which is just the same as the previous, but then we add U1. And then we put the next one, which is just the same as eigenvalue problem, but add U2, and so on. So always just add previous vector. So far it's just suggestions. So let's say that we have eigenvector. Okay, let's try to solve this one with the previous one that we put here. If we find if the solution exists, we try to put it here and try to solve the next. If the solution exists, we try to solve the next. So in principle, the first you always have. So in principle, you can try to solve the next one until you can do this. So this at certain moment it will stop. So it will always stop at the moment when it cannot be solved anymore. For any uk plus 1. So for any vector, so at certain moment we stop. So this is what's called Jordan chain. So this is Jordan chain of equations or Jordan chain of generalized eigenvectors, which we just keep solving until we cannot do anymore. So the Jordan chain will give you the k vectors. So you can clearly see that if U1 is non-zero, because eigenvector, then all of them are non-zero. In principle, they're all complex, right? Because eigenvalue in principle complex. So now what we can do is we can formulate a proposition. Proposition tells that whenever you have a Jordan chain of vectors, of these generalized eigenvectors, you can find solution with these vectors. So you don't need only eigenvector. You can just use all these vectors and form a solution. So proposition tells that if you take x of t as a linear combination, so first we know that this is a solution. This is just eigenvector by exponential. This we know. But then you can give you another one, which is u1t plus u2 lambda t. I can find another one. Will be u1t squared over 2, u2t plus u3, and so on. And the last will be cn, ck, u1 t k minus 1, k minus 1 factorial. So this is a solution of our problem, x dot equal ax, for any coefficients. So this proposition tells that you can, with these vectors, you can find many different solutions of the same problem. And let's just prove it. Let's just check. The verification is by just substituting and looking that it works. The proof. So we can make it term by term. So let's first consider the term which is multiplied by C1. And this is we know. So x of t equal u1 exponent lambda t. Then x dot is lambda u1. Let's e lambda t u1. And ax is a u1 lambda t. This we know this is lambda u1. So this and this is the same. Second term. Let's check that this is a solution. So here, x dot, you have time here, and you have time in exponent. So there are two terms. So the differentiating exponential give you lambda. So it will be lambda u1t plus lambda u2. And taking derivative of the second gives you plus u1 lambda t. Then let's put it all inside. So it will be lambda t u1 plus lambda u2 u1. Okay, and then we have to check what is ax. It's a by this, right? So let's already put a inside. So it will be a u1 t plus a u2 But A U1 is lambda U1 from the first equation. And A U2, remember it's lambda U2 plus U1 from the second equation. And now you see that this is the same. Etc. So then you can complete the proof just checking it for all other coefficients. Well, the rigorous way will be by induction. So we proved it for the first, second, then you can prove it for arbitrary, or by induction, or directly. Doesn't matter. You don't need even induction. So I'm not giving it for a general term, but you can check that. For just the same way, you just compute derivative by definition with respect to time. From on the left, on the right, you take the product and then use equations for the Jordan chain, and it turns out to be the same. So, this is so we get more solutions. So we got more solutions which are now not only defined by eigenvectors but also by generalized eigenvectors. And so then the question is, do generalized eigenvectors form a basis in our space? So the eigenvectors in principle do not form a basis. We see this example. But the question if generalized eigenvectors form a basis, because if generalized eigenvectors form a basis, we have probably sufficient amount of solutions to form a general one. So that actually the answer here is yes. So we are almost close to the answer. And now let's see why yes. So that why yes, and this is now related to this central theorem of linear algebra, which is a theorem of the journal canonical form. Okay, so let's first formulate a theorem which is a corollary of Jordan's theorem. That we will also formulate later. So it just tells you that one can choose generalized eigenvectors for each eigenvalue such that they together for all eigenvalues form a basis in Cn. So you can choose n generalized eigenvectors which are linearly independent. Okay. So let's see what actually it means. What actually it means. So let's make this construction explicit. So first let's write the vector form of the Jordan chain. So let's take this Jordan chain. Remember what it is. And now what we will do, so we will take, so on the left you have matrix A, right, which is n by n. Then it's multiplied by different vectors, and we put them just one after another. So u1, u2, until uk. So let's put them as columns of the new matrix. So this will be n, which is size of the vector, and by k, which is number of vectors, right? And on the right-hand side, we have vectors with different coefficients. So then this right-hand side you can write as the same matrix of generalized eigenvectors taken as columns. And then multiply by what? So first you should get u1. So you should put lambda 0, 0, 0. Oh, no. 0, 0, 0, like this. So taking the first column, multiply, you get just u1. And here the first column will be a1 u1 equal lambda u1. So the second, for the getting the second row, the second relation, so it will be the second column because u2 multiplied by a, and here we should get combination of u1 plus lambda 1 plus lambda u2. So here you should put 1 lambda 0, 0, and so on. So the next will be 0, 1 lambda until the last will be this. So what we get here is what we obtained on the last matrix is called Jordan block, and it has a size of k by k. You see, no? So Jordan chain can be written as a Jordan chain written as a matrix. By A is the same piece multiplied by the Jordan block. The Jordan block is, let's have Jordan block. Let's call it J k of lambda. It's the block where you have lambda on the diagonal, and then you have 1 on the next. And its size has a size k. And this let's call, so in other words, we wrote it A by this k equal 1 j. That's a matrix form of this system of equations. So what the theorem tells is that that you can find for each for different eigenvalues you can form a matrix where you can find the Jordan chain for eigenvalue lambda 1. So for each eigenvalue, you can find the Jordan chain. So the first, the Jordan chain, which corresponds to eigenvalue lambda 1. Then you can take the Jordan chain corresponding to eigenvalue lambda 2. Etc. Such that this will be n vectors in total. So the theorem tells that you can choose Jordan chains for different eigenvalues such that this form a basis. So you can form n vectors of this size. So this is for lambda 1, lambda 2, lambda 3. In principle, this doesn't mean that all lambdas are different. So for each eigenvalue, you can find one Jordan chain or several Jordan chains. But important is that these all vectors will be linearly independent. And then what you get from here is that whenever you multiply A by C, it's the same as C multiplied by J, and this J is a matrix with a J K1 lambda 1, J K2 lambda 2, J, and so on. So you can form generalized eigenvectors in the matrix C, which is n by n. And since each piece, each sequence is a Jordan chain, so it has corresponding eigenvalue. And for this matrix, this equation becomes, take this form. AC by CJ, where J is this diagonal, log diagonal matrix with Jordan chains. So in other words, this will be matrix which is lambda 1, 1, lambda 1, 1, lambda 2, 1, 1, and so on. So this is what's called Jordan canonical form. So we're almost done. Almost done. The only what is missing is now you see that C is a matrix made of linearly independent eigenvectors. So C is a non-singular matrix. So what you can write is let's flip it, put J on the left hand side. So it will be Cj equal AC. And now we move C to the other side. So that's final expression. And this is what the Jordan theorem tells you. That for any matrix A, there exists a non-singular complex matrix C such that when you multiply by this matrix C on C minus 1 on two sides is a Jordan canonical form. So actually what theorem proves is that you can find this matrix C such that if you multiply from both sides, the G will have this structure. So this is a non-trivial theorem from linear algebra that usually in our course, I think it's the end of the course, so where you prove this theorem. Or at least it's one of the hardest results. And all what we did before follow from this theorem. Because whenever you say that you have this matrix which satisfies this equation, it means that this equation is satisfied. If this equation is satisfied, you automatically know that the columns of this matrix C form Jordan chains. If they form Jordan chains, they satisfy all these Jordan chain equations. if they satisfy Jordan-Chase equation, they give you the solutions of this form. So backwards from this theorem, we find solutions of this form. And now, so now we can write the final corollary. Is that a general solution of the system there is a linear combination of solutions. Let's write them. Let's call this solution to be a star. So a linear combination of this solution star for all Jordan chains. For all Jordan chains from Jordan theorem. So if you can take all these Jordan chains from Jordan theorem and form these solutions, they all together will give a general solution. Why? The proof is very simple. First of all, we know its solution, but so we have to check that they give the arbitrary initial condition. It's because x at 0. So for the so what is the x of 0 for the solution star? For a solution star, x of 0 is what? So when you put t equals 0, all exponents become 1. So it becomes c1 u1. This is 0, so c2 u2, 0 0 c3 u3. You see, so everything cancels. So you get just simple expansion in vectors. This is just basis expansion. So we know that since all the Jordan chains together form a basis, so you can satisfy initial condition. So that's so you see it's kind of not a simple thing, because so what is the idea is if you want to solve this system A dot equal AX, eigenvectors are generally not sufficient. You can find, you should work with the Jordan chains. In principle, what is important is that the solution of this Jordan chain equation is not unique. So the only thing which is Jordan theorem tells is that those are solutions not unique, but you can choose them in such a way that you get a basis. Whenever you have chosen them, they make a basis, you take this sum of the solution of that form, you get this general solution. So that's a complicated way, but it gives you the full answer. So we will see next at the next lecture. So what this answer means for the system. So how it describes the different solutions for in different situations. So already this physical interpretation. But before that, let's just give one example where we just make before this, let's first make observation and then make example. The observation. So observation is so each block, so each Jordan block of size k by k corresponds to k eigenvalues, k equal eigenvalues, lambda, because it's clear, no? Because it's block, all lambdas in diagonal eigenvalues. So it corresponds to k eigenvalues lambda, but just one eigenvector, because only one this block only has one eigenvector. If you subtract diagonal, you can only solve it with 1, 0, 0, 0. So what it means? That means that if the algebraic multiplicity of the eigenvalue is, so consider some eigenvalue. In the Jordan eigenvalue, in the Jordan form, it should appear in one of the blocks, only several blocks. So algebraic multiplicity is just sum of the sizes of corresponding blocks. And what is geometric multiplicity? So each block just gives you one eigenvector. So geometric multiplicity is how many blocks you have. It's a number of blocks. And since each block is at least 1 by 1 or more, then it automatically means that geometric multiplicity is smaller or equal than algebraic multiplicity. Because algebraic is the sum of the sizes of blocks. And this is just number of blocks. Of course, this should be at least bigger than. Do you see it? No? Okay, so let's put example. Example, and we end. So let's make the whole program for matrix A equal minus 2, 0, 0, 1, 1. And solve, let's solve this equation, x dot equal x. So x, 3-dimensional. Okay. So how you proceed? First, find the eigenvalues. So we have to write characteristic equation. So this is determinant minus 2 minus lambda, 0, 0, 0, 1 minus lambda, 1. Okay, so how you should remember how you find determinant. So this is block diagonal. So it's this term multiplied by this determinant. So this by this product minus this by this product. So it's minus 2 minus lambda by this product will be 1 minus lambda minus 1 minus lambda. And then minus this part, so minus plus 1. So when you open, 1 cancels here, lambda cancels, so it will be lambda squared just. It will be only lambda squared, so it will be minus 2 plus lambda lambda squared. Okay. So there are two eigenvalues. So there is one eigenvalue which is -2, and another is 0. There is -2 and 0. So lambda 1 -2. So we have one eigenvalue lambda 1 which is -2, and another eigenvalue lambda 2 is equal to 0. Okay, so let's start first with -2. So that's eigenvalue which is simple, because algebraic multiplicity is 1. It just appears as one root. So we know there will be one eigenvector. So let's write eigenvalue problem. So we subtract -2 from diagonal. So we add 2 to the diagonal. This gives you 0, 0, 0, 0, 0, and then we have to add 2. So it will be 3, 1, -1, 1. And we find that eigenvector will be, for this eigenvalue, the eigenvector will be 1, 0, 0. Okay. And we have a solution. Solution will be arbitrary coefficients, let's put it 1, by this vector, and by exponent lambda 2, so -2t. This is a solution. Okay, next let's consider eigenvector lambda 2 equals 0. So this is double eigenvalue. There are two roots. So algebraic multiplicity is 1. Okay, so then first we start with finding eigenvectors. So now you subtract 0 from a diagonal. So it means that you just don't change the matrix. 1, 1, -1, -1. So what is U? So you see, first of all, if you want to cancel this row, you need to put yes. So if you so you multiply like this, right? So you first yeah. So if you cancel this row, you should put 0, which cancels. So first term should be 0, yeah? Because otherwise the first row will be not 0. So the first term should be 0, and then the sum of the two components should be 0, because it's 1, 1, -1, -1. So this is a possible solution. And so what you can check that it's only vector. There are no other eigenvectors. So whatever vector which you obtain from this equation is multiple of this. So do you see that geometric multiplicity is 1, which is smaller than algebraic, which was 2. So in that situation, we know that in that situation we already have just one solution from here, one solution from there, so we need to find generalized eigenvectors. So in this case, we need to go to generalized eigenvectors. So what we do, so we call this first eigenvector. So we give this number 1. And we have to look for the generalized eigenvector. So we have to solve. So let's not put 2. It's not necessary. So we have to solve the next equation. Like this. Cool. So lambda, our lambda is 0. So we have to solve equation AU2 equal U1. So now let's write what is AU2. It's minus 2, 0, 0, 0, 1, 1, minus 1, minus 1, U2. And it should be 0, 1, minus 1. Solution, again, is not unique, but we can guess it. So we can guess it in such form. So you get 0 here, so first component should be 0. This is certain. But then if you want to get this vector, you can just take this column, right? You just take what? 1, 0. And in principle, we don't even have to do anything else because we already see that this, and these vectors, so this U1, U1, and U2 are linearly independent. So we already have 3 vectors, this, and that. They form a basis. So we are done. So we don't need even to check if you can check that you cannot actually you can check as an exercise that you cannot continue. You cannot continue, but this is already guaranteed by Jordan theorem. You cannot continue. Otherwise, you will get more generalized eigenvectors. But anyway, so you can check that you cannot find the third one, but we're already done. So what we have is that the proposition, the solution star, remember solution star will have the form x of t equal eigenvector with arbitrary coefficient plus another plus C2 by U1 t plus U2 E lambda t. So this is our solution star for the eigenvector, generalized eigenvector. But now remember that lambda is 0. And this gives you C1, 1, U1 plus C2 U1t plus U2. Because exponent is 1. So we have this solution, and we have this solution. And our corollary tells that take the sum of solutions for all eigenvalues, and with the generalized eigenvectors, you get general solution. So let's check that it works. General solution is this C1 is this one. And let's just put U1 explicitly. So it will be C1 by exponent minus 2t by 1, 0, 0. Okay? And then that solution at the end, plus C1 by the vector U1, which is 0, 1, minus 1. Plus C2. And this will be U1 by T. So it will be T minus T here. And then plus U2. U2 is 0, 1, 0. That's it. That's the general solution. So let's check. So initial condition. What is x at 0? Exponent, this just becomes 1. And this is C1 comes here. And then here we'll have 0, so it will be C1 plus C2. And at the end will be, this is 0, so it will be C minus C1. Gives uniquely these three coefficients, right? So whatever initial condition, C capital 1 is the first component, C1 is the third component, and C2 is obtained from the second component. So given initial condition, we have three coefficients, and this gives the solution. So that's how you find a general solution in general. So that usually it's not so easy thing, because you need to form the full Jordan form. So usually all eigenvalues are simple, are different. Then it's easy. You just have some of these eigenvalue solutions, eigenvector by exponent eigenvalue t. But if there are multiple eigenvalues, in a very general form, you should find Jordan canonical form, which gives you generalized eigenvector. From generalized eigenvectors, you cook up these special solutions. Their sum is a general solution. So that's a way. So that's a way how you proceed generally. In practice, it's normally much simpler because almost all eigenvalues are simple. So the actual Jordan chains, they are not so complex, they're not so large, but they occur, and it's very important to know what they are, because they define different physical phenomena. In fact, so there are many phenomena, not only physics but in other areas as well. So where the Jordan chains, they actually responsible for something interesting what happens in the system. So we did mathematical part. So the next time we start we still have some mathematics left, because this is we now know that linearized problem we can solve. There are two things which left to understand the connection between linearized and original problem, and then understand what it means for the oscillations of physical problems. So we also have physics and also a bit of mathematics. So that's we will continue tomorrow and after tomorrow.